Good afternoon. Welcome to this Antonio Picariello lecture on data science. Thank you, Dr. Quartulli, for being here, and thank you to everyone. Please, Professor Longo, the real coordinator of this lecture of the data science master degree. Please, Prof. Longo, can you introduce the lecture?
Professor Longo is a real, stop.
No, Professor Longo is real in the sense that he is not here. That's the only reality I have. Let's say that I am glad of these lectures because allow me also to see, even though virtually, even in this bad period, friends with whom we were used to meet all over the world for various meetings together with Marco Quartulli. We are at our second European project together, I think. So it has been a collaboration which started more than 10 years ago, I will say, at this point. Yeah, we are getting old, Marco. I am getting much older than you are, but much older than you are. It's a differential, you know. And I am very pleased because one of the most beautiful things about our work is the fact that you are allowed to meet interesting people, to make interesting friends all over the world. And Marco, among the other things, is also hosting 2 our students for an internship, trainship at Vicomtech in Spain. I'm sure he will tell us about Vicomtech. He's from the south of Italy. He was born in Bari. Quite a few years ago. Let me say that his PhD, his laureate was in 1997, so he's very young in comparison to me. He has a PhD from the University of Siegen in Germany, obtained in 2005. Then he has been researching in various companies and starting from remote sensing, ground segment engineering, then to image analysis, archives and mining with advanced computer system in Italy. Then for a few years, he worked with the image analysis group at the Remote Sensing Technology Institute in German Aerospace Center. And finally, 10 years ago, he joined the digital television department at Vicomtech, researching on big data analytics and for the multimedia and geospatial analysis domain. Here, I must say that this type of lecture are particularly close to my heart because Professor Picariello was our guru for big data and everything related with it. And therefore, you have a great responsibility tonight because you are speaking of something which was very close to the heart of the man to whom these lectures are dedicated. So Marco, I make this introduction short. I'm glad you are here and I'm looking forward to your lecture. So the stage is yours.
Thank you very much. Thank you very much. So I hope you can see the cover slide of my presentation.
Yes, we can.
And let's say I will be trying to address issues of visual interaction and communication in data science. And what I mean by that is I really am trying to discuss issues, to reflect upon issues related to visualization in the sense of visual interaction and communication between human experts and machine learning and models in general. The idea is we are spending significant amounts of effort on the one hand to transfer expert domain knowledge from humans to machines. That's expensive. You know, it really looks like we have been able to solve issues related to image understanding, for instance. that has come with a price, in the sense that has required the definition of a tagged corpus of image content that would be probably impractical for a single entity to put together. And that's important. We need to reduce the barriers to the adoption of data science, machine learning, artificial intelligence. And one important barrier is the cost of training data. So we need to lower the cost of the communication between a human expert and the machine. At the very end of the process, after we have looked into descriptive statistics, all the way to prescription, perhaps, we will have a machine that has built a representation of the game, if you wish, that we as humans are playing. For instance, a game of optimized management of a plant producing ice cubes in somewhere in the world, only using perhaps renewable technology, renewable sources of energy and materials that might be continuously interrupted, that might be very irregular. That's a complex game. The machine might have learned well how to play that game by building internal representations of the game. At that point, we will need a step beyond prescription, and the step will be communicating back to human experts the strategies, the policies, the optimal policies, if you wish, devised by the machine. In this sense, interaction and communication between human experts and machine experts is a crucial matter. And visualization is a way to address this kind of barriers, both in input and in output. And my reasoning today will be structured in two parts. The first part will be related to exploratory data analysis, how to think about data exploration, how to start the process of exploring a data set through visualization. Whereas the second part will be around visualization for presentation, for decision making, for operations in a way. Start with part one, of course. And the picture I used to represent that part is this house with colored windows. To make it very short, the idea is that we have a phenomenon that is in a way partially known, a mysterious phenomenon. We cannot observe it directly. We can, though, perform measurements on it. And we can try to combine those measurements to obtain different model-based views of aspects of this phenomenon. And let's say the different colors in the windows in our concrete block housing the mysterious phenomenon generating the data represent exactly that. Now, for part one, therefore, we have the phenomenon. We are able to have an idea about a direct model that is able to generate a data set from the phenomenon. The inverse process, the model inversion, that generates a model view, perhaps a parametric description of the model that, for instance, most probably generated the data, is exactly what we are trying to accomplish, what we will be trying to accomplish after, let's say, this exploratory phase. And essentially, the different colored windows, the different visualizations, each one will be highlighting specific aspects of the phenomenon, exactly because each one will be, in a way, casting the data onto an implicit or explicit model of the phenomenon. So that's the first thing. Banally, you never do a visualization. Perhaps there often is no single ideal visualization. Let's say an important thing to consider is that multiple views of a data set tell us different stories about the phenomenon that generated the data. Hopefully the stories will be reinforcing each other, will be confirming each other, but we really need those multiple views. The obvious question to ask is, who is the client in explorative data analysis? And the answer is the client in EDA is the analysts themselves, in the sense that what we are trying to do is we are trying to get a feel, we are trying to you know, get an introduction, if you wish, to the data. I skip forward to the conclusions of part one. Essentially, what I am hinting at is to visualization as communication through a noisy channel, in the sense that we have this phenomenon that is generating measurements. Those measurements are represented in a physical artifact, if you wish, a visualization or a set of visualizations. A human is observing that visualization and gathering ideas, gathering internal representations, if you wish, of the model. The issue we face in choosing what visualizations are significant is a matter of appropriately selecting visual coding, considering the typically implicit underlying models in each visualization. So essentially, we have a problem that is related to the problem of communication through a noisy channel. Okay, now, building visualizations to represent models is essentially older than mathematics itself, and of course it's a topic that has been investigated for a long time, and in particular since the popularization of you know, so to say, interactive and displays. The idea tends to be that a materialized view that can be manipulated is a basis for communication, reflection, and discussion. And of course, a few points related to that are the fact that Visualizations probably do not exist in isolation. The textual component of a notebook, of an analytical notebook, is there to support a critical interaction of the readers with the material, as well as, at least in the explorative phase. Of course, slightly different considerations will be in place for the second part of the talk, where perhaps the textual part might be there to indicate, to propose ways to interpret the data. But really, on the one hand, text represents, let's say, a more critical, if you wish, communication channel, perhaps self-communication of the analyst with themselves, in the sense that really text and images are complementary also in the way in which they are analyzed by readers. And as I was telling you before, with the picture of the windows, one visualization is typically not enough. Each diagram is a model-based filter, and multiple models might be relevant. And we really need to start building a model in a way through visualization. So it's important to be explicit as much as possible about assumptions and verify them as thoroughly as possible on the data. And then, of course, there's the issue of how this visualization activity looks like in the case of small data versus big data. A very short consideration, a very short way to address this point is that really for big data, things tend to be harder and more critical at the same time. Of course, there are issues that are specific to the visualization of very large data sets. A banal consideration refers, for instance, to the issue of occlusions. You could easily saturate a visualization by representing even hundreds of thousands of points, typically. So you really need, in that case, to consider the fact that it's the details that entail, that produce most of the value of the analysis. And what I mean is, you might have phenomena that fall into, let's say, abnormality, into, you might have lots of like, you might have 100,000 light curves that you are representing, and most of them might fall into, I don't know, 100 kinds of normal behavior. Now, the thing you do not want to lose to, for instance, random sampling, are exactly the strange ones. The strange points in a data set will always be the ones that are either things to be corrected or things to be discovered and amplified. So again, there is a need there to really integrate deeply visualization and data analysis. And also, visualization is often, for very big data sets, more critical than in the case of small data, exactly because visualization is let's say, hard to substitute in a way as a way to get acquainted with the data, as a way to have a first glimpse into how the data looks like. And this is the standard example, the standard motivating example for visualization. I'm sure you've all been exposed to it before in your courses. If you haven't, this is the story. We have a table. The table includes 4 groups of 2-dimensional points. Each point has an X and a Y coordinate. Now, the 4 groups have a mean, exactly the same mean in the X coordinate, exactly the same mean in the Y coordinate, exactly the same variance in the X and in the Y coordinate, well, almost exactly. The correlation between X and Y is the same in each case. The linear regression line is the same in each case. And yet, the 4 groups are, although we can extract a number of descriptive statistics from the 4 groups that are again model-based representations of the phenomena, if you wish, that generated those data. If we simply plot out the 4 groups, we immediately notice how there's more to this story. Really, there's a richness in visualization that really helps us make sense of the richness of the phenomena that are expressing the data. And yet there is more. Once we have this visualization, the question becomes, look, let's play a game. I am taking the visualization and I am showing them to you, and I'm hiding the data. And the next question will be, could you please fill in estimates for the values of the data points that you are observing in the picture to fill up the table on the right. So once again, I hope I am not. I'm hoping I'm being clear. Let's say from the data we generate the visualization. It's important to be able to go back. It's important to be able to invert the visualization and go back to the data. Either really go back to the data points or simply go back to functional representations of the data points. And this is what a lot, this is really, let's say, a key point in this line of reasoning that I'm trying to propose to you today. This invertibility is an important factor. And that again goes back to the issue of, you know, being able to exercise critical reasoning. What I mean is that if you are trying to build a misleading visualization for marketing purposes, for instance, it is clear that you will tend to build a visualization that generates in the mind of the reader, in the mind of the observer, a set of data points that have little relation to the original ones, that might overrepresent, for instance, some of the issues you are trying to push. Really, the ability for the observation to be inverted is an important one for scientific purposes. And so let's look into the issue of how do we proceed? How do we look into the issue of visualizing a dataset? And we'll look at it in terms of a set of boxes, a set of transformed datasets if you wish. We will start from the source data and then generate the right data and then visual abstractions and then a visualization from that. We can also look at the process dually in terms of the transformations between the data representations. So there will be a data processing and transformation step, a visual encoding step, a rendering step, a perception step. And of course, the observer will most probably need to reflect back on each one of the transformations in order to obtain a better product, if you wish. Now, in terms of blocks, we have source problem data, which typically will be domain dependent. I'm not going to tell people who are working on in data science or studying data science in the programs such as this about the issue of cleaning data, of really refining the dirty side of of an input data set. The abstracted data and models, though, will need to be associated to visual representations. So once our data set is for instance, cleaned in the sense of once outliers have been properly managed, once data imputation techniques have been adequately considered, the clean data set will be transformed to a visual representation. That's what we'll discuss in detail. And once the visualization is obtained, a complex sense-making activity will be possible, and a final short story in this presentation will be how to try and observe this complex sense-making activity on the part of the final user. In terms of the arrows, in terms of the transformations, of course, in the beginning we will have data wrangling activities, abstraction and processing, then this mapping of attributes, of data attributes to visual variables, to visual marks and channels, then the rendering of the image, and then again the perception and visual thinking by the user. So once again, let's look into the beginning of this story. Well, beyond the standard data wrangling activities, really a good thing is to look into the basic structure of the data we are looking into. We are all very familiar, I guess, with tabular formats. There are very different ways to think about the data. For instance, with respect to the relations between the records, the instances we are looking at. There are ways to look at the data that emphasize certain, for instance, spatial attributes of the data. Most of what I will reflect upon will be dedicated to tabular data. and at some point we'll also consider the issue of networks and trees. But let's for the moment consider tabular data. Now, in a tabular data set, finally, let's consider that each row will represent a record, an instance of a measurement, of a multidimensional, if you wish, measurement. Attributes will correspond to columns. So each column will will have a different nature. Some columns, some data attributes will be quantitative, or categorical, or ordinal, and even the ordinal ones might be sequential, diverging, cyclic. And of course, that's an analysis that we need to carry out well, before we can map those visual attributes, sorry, those data set attributes to the visual ones. And of course, there are lots of other considerations that might be important in the cases in which really the important part of the data set is not in the structure, in the single, if you wish, instance, but rather the crucial part is the relation between instances, a hierarchy, or really the relations between items. But again, the crucial part again will be taking this table, analyzing the content of each column, and then trying to generate a visual mark for each row of the table. Those visual marks will be essentially glyphs, will be standard elements of a visualization, either points or lines or areas. Now, points, lines, areas, etc. have attributes in and of themselves. Points have X and Y positions. Perhaps they have a color. Perhaps they have a volume. Sorry, an area, or a saturation of the color, or a size, etc., etc. So an important part of the visualization, of the visual design game is the invertible mapping, is the mapping between the columns in a tabular data set and the visual attributes of the marks that represent the lines. Typical example, basic example, the Gapminder visualization. Here we have a table in which each row represents a country, well, a country, in this case in 2006, as you can see from the title. Each country has a name. It belongs to a continent. It has a population in millions of inhabitants. It has a gross national income per capita. It has a number of an indication about, let's say, the health of the inhabitants, in this case the number of children dying before age 5 per 1,000 live births. And the issue is, can we convert each one of these lines in a visual mark in a representation? And you can see that that's indeed possible. Now, we really need to take in this visualization and start considering what what in fact has been done here, it is very clear that an alternative visualization would, for instance, take into account, well, for instance, it might group countries by continent, by representing, I don't know, European countries on the far right and well, Eastern countries, if you wish, on the far right, and American countries on the left, as we do in, you know, a standard planar map here in Europe, with Europe in the center. Here, instead, the chart designer has chosen to represent the way a country belongs to a continent by a color. How come? Why is that the choice? Why are money and health chosen as X and Y coordinate? A different example, recipes. Each dot represents a spice, an ingredient in cooking recipes. Here, what's important is the fact that two ingredients coexist in a given recipe. That's not, well, both of these visualizations have very practical value. It was very evident in the case of Gapminder here, because really it allows following, understanding, let's say, the history, the evolution of countries and health and economical systems in the world. Here, imagine, well, something that happens is you get contacted by a company that is trying to expand to a new market. The company is perhaps producing some specific ingredient that is typically used, let's invent, in Spanish cuisine a lot. In order to be able to expand to Italian cuisine, perhaps, they might be looking into ways in which really their ingredient, their node, is connected to other ingredients in the graph. So if let's say cheese is used in Spain in the same way in which I don't know, a dessert is used in Italy, then perhaps there is a space that can be considered for expansion, and that space is exactly the space of relations between ingredients. In this case, as you can see, again, the categories are represented by colors, and then there's a prevalence of the ingredient represented as a dot, as a node size, but the fundamental content of the visualization is relations, is the way, is the number of shared compounds, the number of shared recipes. And you see, though, that even though that's a very, that's really the key content of the visualization, you see on the bottom right how this content is simplified in dramatic terms. We don't see a lot. We only see 3 levels of sharing. You see there's a 10, a 50, and 150 shared compounds. So a dramatic quantization has been applied on this crucial piece of information, on this important attribute of the dataset. How come? How is that? And well, that's a very, very similar example. And it's, of course, co-occurrences of characters in a novel. And again, it's a different way to represent relations. And here there is a twist in the data set, in the sense that one of the attributes is not an original input of the data science process. One of the attributes, the cluster, the color, if you wish, of the hue, sorry, of the cell in this essentially concurrence matrix. So it's an alternative view of a graph again. But again, this element is already representing the output of a rather complex piece of modeling. So we are not only considering the original data, we are also considering, obviously, intermediate products in our analysis pipelines or in our analysis procedures. Now, how do we decide how to represent the lines in our data frame, if you wish? How do we decide that health will be on the y-axis and money on the x-axis in the Gapminder visualization? There are two important principles to take into account. The first one is the expressiveness principle, and it states that visual information should express all and only the information in the data. If, for instance, ordered data should not appear as unordered, or unordered data should not appear as ordered. The idea is that we can always add fake information to make the visualization more appealing. That's the typical case is building pseudo 3D visualizations by putting data in a 3D view when you do not have a third dimension, a third numeric attribute to represent. Again, the observer is given the visualization and the empty table whose values should be filled in by observing the visualization. If we give them a visually appealing representation that contains completely irrelevant, completely fake, completely, well, information that does not come from the phenomenon we are trying to represent, but simply from the design process, then the data that is filled in the empty table, in the inversion process, will not look like the original data. And the second story, the second principle is the effectiveness principle. The importance of the information should match the salience of the channel. Now, what do we mean by a channel? In the case of a two-dimensional representation, such as the Gapminder representation, we have essentially points on a plane. Points on a plane can be represented by, well, have as key characteristics their position on the x and y scale, their position on a very well-known and fixed and common scale. If we were to consider areas, for instance, such as we have seen in the Gapminder visualization, we would also add an area to those points. And since the points are colored, we would also add a color hue to the set. And we have seen in the Les Miserables example, we can play with color saturation as well. And of course, lines would have a length and oriented segments would have a tilt. Now, each of these attributes represents or is essentially a channel, a visual attribute of a mark, of a graphical mark that we can change and that we can map to an attribute of the dataset, and that we can change to represent those attributes. Some of the attributes will be better for categorical attributes. For instance, color hue, as we've seen, tends to be used with categorical attributes. We'll look at why in a moment. But we also have to consider the fact that we might be better at inverting correctly some of the attributes of the marks with respect to others. Again, we are given the visualization and the empty table and the job of filling in the table correctly by looking at the visualization. The question is, would we be able to do that independently of the mapping between the attributes? Let's see. We can look at the effectiveness issue by considering the points such as the accuracy, that is how accurately the values in the table, in the empty table, can be estimated by looking at the attributes of the visual marks that we have employed in the visualization. We can look at we'll see, for instance, to start giving out the let's say the end of the story, that for instance, things like colors or things like color saturations might be harder to transform back accurately to the original values, because a red that is very, very red will be hard to quantify with respect to a red that is grayish. That's also a matter of discriminability. How many different values can be perceived? You remember that continents were associated to colors. So it was easy for us to discriminate 6 colors, right? The 6 continents. The groups, the clusters in the Les Miserables visualization were about 6 as well. In the case of the recipes, again, we had around 8-10 groups of recipes. Would we be able to effectively discriminate between 500 different colors, or would we confuse them? It's really an issue, right? It's we need to think about that when we are trying to assign, for instance, a continuous numerical attribute to a color. There is the issue of separability. We'll look into it in a few slides. And then there is the issue of how useful a given mark attribute is in letting us see normality and anormality, if you wish. Again, since the value is in the outliers, how easy it is to spot some values from the rest, and how good the channel is in conveying groups, in conveying types of normality. Now, with respect to accuracy, there is this thing in experiential psychology called Stevens law. Steven apparently tried to experiment on exposing human subjects to different kinds of stimuli to verify how well they were able to quantify the input of the stimulus. So how objective, how quantitative, how linear humans were. And for instance, he was converting numbers to a loudness, or to a brightness, or to a length, or to electric shocks, as we can see on the left. And what he found out was that some things were judged logarithmically. People were saturated by smells, and therefore progressively they were less able to tell them apart. Whereas they tended to overestimate electric shocks, and essentially they were tending to overemphasize the differences. Length, instead, was more or less linear. Let's say this is important in the sense that to stay with saturation, length, area, depth, and brightness, some stimuli tend to be linear, and therefore the mapping, the inverse mapping from the visualization to the empty table would be effective, in the sense that differences would probably not be overemphasized. There would be a linearity, let's say, in this inverse transformation. Brightness, instead, would die out, would entail, would determine a progressive devaluation of differences. Again, we are just trying to generate h hat, that is an estimate for the hidden data set from the observations we have. And there's essentially an exponent that is attached to each visual channel. And lengths tend to be linear, and saturations, for instance, are around 2. So we'll risk an exponential rendering, if you wish, of the data set onto the visualization. And it might be hard to invert this law. And then there's noise, of course, there always is. And in this case, each channel will be progressively noisier. And in the 80s, people were trying to quantify the error. In this case, they were considering, they were measuring and really modeling normal and additive noise. I wonder whether let's say the additivity is always verified, and normality as well. But let's say some visual attributes are noisier than others. And really, that's very related, of course, to Stevens' law, but that's something that we need to take into account. Positions with respect to a common scale tend to be both the most linear and the least noisy of the visual marks. And so again, quantitative channels are different in terms of expressiveness, And then there is the issue of how many different values we are able to discriminate. You remember that in the recipe visualization, we only had 3 levels of co-occurrence, co-occurrence in well, 3 levels, 3 numbers of recipes in which 2 ingredients were happening, were present at the same time. Here again, we have a volume of exchanges between countries, and the relevant part there is really how quantized the arcs in the red graph are. So how little nuance we can expect to pass through the filter of a visualization such as this one. And the same goes, of course, for color, how hard it is for us to discriminate more than around 16 colors in a visualization, perhaps less. Things get so hard when we have many attributes in a data set, many columns if you wish, that it might be worth it to consider trading color with space. And that's where a trellis plot comes about. A trellis plot is just the idea of trading, of giving away space, or producing much smaller plots, so less precision if you wish, in X and Y, in order to be able to avoid, if you wish, some of the complications of color. And the complications of color include complicated stuff, like, for instance, the fact that the perceived brightness depends on the hue of the color. So reds and yellows might inherently look brighter than blues and greens. So there really is a matter of separability of the channels. Here really there might even be a matter of interference between the channels and potentially even between the rows of the dataset. So representing very rich datasets with a number of columns is a complicated issue. In part 2, we'll be trying to look at ways to address that through multiple interactive views, for instance. But to close part 1, essentially, in order to serve ourselves as explorers of a data set, we really need to look into the issue of inverting the phenomenon that is generating data by applying different windows, different model-based views on the data, so that we can reveal different aspects of this unknown phenomenon. That's perhaps the key message of part 1. And in order not to cheat ourselves, in order not to, we need, in order to be scientific, let's say, we need to be vigilant about appropriately selecting visual coding, trying to hide and deceive ourselves in the least possible way. And that concludes part 1 of the talk. Part 2 will be about, or is going to be about visualization for operations. You see, we are going from having a mysterious phenomenon that we look at by looking at a number of colored windows to something much simpler. The number of models seems to have reduced substantially, and there is a very different sense of purpose here. There are controls next to the visualization that are meant to help us really operate, manipulate, manage the phenomenon, the mysterious phenomenon, by interpreting what we see through these visualizations. We are transitioning from exploratory data analysis to task-oriented visualization. Here, really, we want to propose in a way or to help decision makers define actions that are interesting based on the models that we have. We are proposing them. The client, therefore, is not anymore ourselves or the analyst, but rather a client that will be in charge of taking decisions on the phenomenon of interest. And again, spoiler, we'll see in this second part of the line of reasoning of the chat that testing will be very important, and that it will be important to try and follow the user in their steps, to try and understand how they are navigating the linked views that compose our car driving dashboard. And then it will be essentially about organization and design in the sense of organization. So we were discussing the ways in which channels tend to interact with each other in unforeseen ways, in undesirable ways. Well, I'm not sure whether somebody is asking a question.
Usually we ask a question at the end.
Okay, so I'll keep going. So again, the more we add columns, the more we add attributes to the dataset, the harder it becomes to keep them separated and linear, and the harder it is to try and avoid crosstalk, if you wish, among them. So, well, a good strategy might be, let us try to reduce as much as possible the amount of attributes that we are trying to represent in a visualization. Perhaps instead of putting all the columns together in a single visualization, it might be better, again, to build a set of visualizations, of simpler visualizations, and see how we can navigate among them, right? One strategy is what is called high information graphics by Tufte, and the idea is, let us try and reduce as much as possible the information sources that are suspect, the mappings that are doubtful, that in the sense that they either do not represent information that was available in the original data, or attributes that do not represent faithfully, invertibly, if you wish, accurately and discriminably that information. We end up with things like that. In the x-axis, we see date time, well, essentially a day of the year. You see that, that we have a number of months from October 2009 to September, beginning of September 2010. On the y-axis, we have an IP, so an Internet Protocol address for one of the machines of the University of Coimbra. And the designer here is simply trying to represent the volume of packets shared with, well, that have been sent out by each machine. And although this represents a data set, if you wish, with only a temporal index and two attributes, the sending machine, if you wish, so a category, and the volume shared, there's a lot that we see in this visualization. We see that servers are most probably in this upper part of the representation, although most probably some of them might be in this area here, in the lower part of the plot. We can see that some machines might have changed their role. There might be more density in some time frames of the year. We can clearly see vacation days. We can see both the main servers of the university as well as probably departmental servers interspersed with personal workstations. So there is a lot we are able to take out of a simpler visualization that focuses on the basics, so to say, that is trying to simplify the message. Even because, again, things tend to already be, again, let's say, we really need to be looking critically at these simplifications as well. Are these simplifications enough? Will phenomena like overdrawing or the disappearance of points due to low saturation, or in this case we were seeing a lot of binning applied. We had pixels representing quantitative values. So will this binning be adequate for the tasks we are considering? And yet it is clear that this represents a possible strategy to address some of the crosstalk issues we were discussing before. Now, if we have a simpler visualization, we will probably need to consider a number of them, right? We have a simpler view, but then only by considering multiple simpler views will we be able to represent the richness, if you wish, in terms of attributes of the data set we are considering. Now, this is called multiple views in visualization. the idea is that we are trying to take a data set, a data source, if you wish, and we are trying to disperse its contents into distinct views, either to represent different aspects of the same source in different representations, or to see, for instance, different, or to be able to compare the different ranges, different time periods, for instance, different subsets of the data set. There are really, here is where, let's say, a less well understood, a more poorly understood aspect of visualization comes into play. If we are looking at multiple visualizations, then we are implicitly looking at interaction, at the way in which the user is transitioning between these visualizations, at the way in which these visualizations are being used to organize the data, and in the way in which this interaction is being used to coordinate, if you wish, the views, for instance, in terms of selecting areas of interest by brushing techniques, or by selecting subsets of a multi-channel image data set. And that all brings us to trying to gain a deeper understanding of the role of interaction in information visualization. Now, what we really need to do is try to define in a way, in advance, what the trip, what the journey of the user will be through our system. And let's say an oversimplification of this trip is that is nevertheless extremely useful when designing a visualization system is proposed, for instance, by Schneiderman in the 90s. He says that there are only a few things that we can really do in a visualization. We can get an overview of a data set, we can zoom in and essentially identify an area of interest. We can filter out what's inside versus outside this area of interest. We can ask for more details, perhaps for more attributes on the records in that area. We can compare, as we were saying, different areas. We can perhaps extract the output. We can extract the data in the data set we have been in the subsets we have been selecting, and let's say there are a number of competing proposals, let's say, or well, quite a number of ways in which people are trying to define what these interaction techniques can be modeled with. I think the most important thing, though, is that when designing an interactive visualization system, we really start by coming up with a theory, in a way. We try to categorize what the actions of the user will be in order to be able to verify those assumptions, those theories, by following the users in their tracks. The idea is that you are able essentially to closely follow what a number of users have been doing with your visualization system. That you are able to play back, if you wish, their interaction with the system, that you are able to represent their actions and their interactions with the data. And that might be done through things like a Sankey diagram, so let's say a diagram representing fluxes, if you wish, as is done on the left. That will only be, of course, you see on the left, you see very linear, if you wish, very left to right, very simple journeys. It seems like the visualization system there, the system the users are interacting with, have a very definite number of entrances and a smaller and very definite number of exits, of output views, and a very small number of intermediate views, and there are no loops, so people are not typically going back from page 27 in the middle of the diagram back perhaps to page 1, or people are strangely enough not going, well, a very typical thing is that search systems, for instance, tend to be used iteratively. So a very common thing you will see is people on page 4, which is the main output on the upper right of the left diagram in this page, going back to perhaps page 36, so to one of the main pages. That's what happens, for instance, with again, search. People tend to use search systems by progressively better specifying, or specifying in more exact and stringent terms, the query they are interested in. So let's say a back loop will typically be there, and therefore what I mean is that the left diagram is very clear, and yet in practical terms, in the real world scenarios, it will be of limited value, exactly because there will be many connections, and it will be hard to make sense of it. The second possibility is, of course, to focus on the connections themselves, and therefore to consider a diagram such as the one in the middle, in which the key content is exactly the way in which people are transitioning from one page to the other. Now, here you lose the flow, you lose the beginning to end story. You're only able to see the single connections. So in a way, this is not really an alternative to the first one, but rather a complementary view. And again, in order to improve on this visualization of a single transition, you might look into tree-based essentially views, such as the one on the right, that essentially expand these the view in the center to multiple levels, trying essentially to combine the two left ones. But once again, there is multiple views signify or represent multiple models of the thing you're trying to understand, and therefore multiple views, multiple alternative visualization schemes are valuable. They tend to interact with each other, either to confirm models, or let's say modeling assumptions, or to disprove them. So let's say, this idea that visualizations can be used to reflect on a visualization system is something that is done more and more, and that we need to take into consideration. And those views are valuable exactly because, let's say, a finished, if you wish, visualization system still needs to answer a very important question. I designed a visualization system for a database describing the history of, I don't know, an oil refinery last year. And I designed a new one this year. And a possible question is the new version any better than the other? How much better is it, or how much worse? Can I say it is 23.5% better than than last year's version? So the last step is probably the issue of visualization performance evaluation and validation. Now, there are times when the task that we are trying to address with a visualization is so well defined that things are simple. Let's imagine you are trying to find the needle in the haystack, right? Let's say a possible way to address the quality in quantitative terms of my visualization system is to let's say, simply measure the cost of accomplishing a task, of accomplishing a goal by using the two versions of the system, the one from last year and the one from this year. The idea is that by using a better version, users will be able to accomplish the goals defined for the system faster, more accurately, with increased confidence. They will be able to generate more insights, better decisions, etc. And that those things are easy to quantify and to measure. Things are slightly harder, though, than that, because it's very seldom, it doesn't happen often that we are designing a visualization system to do one thing, right? Typically, we are into visualization in order to generate insights, in order to establish this issue of this. We are into visualization as a tool for cognition, and therefore the objective, the task, is not as well defined as we would like to be able to put a number on it. It's not that easy. If this is just a matter of waiting flour to make bread, that's something that's easy to measure. If this is a tool for cognition, if it's a tool for open-ended exploration, as in part one, well, things tend to be more complicated. So complicated, in fact, that models for validation have been proposed that try to decompose, really, a visualization in a nested set of considerations, of elements. At the core, if you wish, of a visualization system, there is a set of algorithms. That set of algorithms produces attributes that are visually encoded and that can be manipulated through an interaction idiom, so a predefined, if you wish, set of interactions, such as one in the lists we were looking at before. All that interaction and visualization serves an let's say, a task that might be very explicit, very well determined, or more abstract, more generic. And all of that will make sense, will be significant in a given domain situation. And the hard part is that we can go wrong on all of these levels. We can build the wrong algorithm, something that really is, takes too much time, or we can build the wrong abstraction, as we were discussing, the wrong encoding, as we were discussing in part 1, or we can misunderstand completely the situation. So that's really an issue, the need to look at the validation of a visualization system in terms of all of these components, observing, considering how they interact with each other in a nested way. So again, with respect to the domain situation, we might be addressing the wrong problem. In order to avoid that, we need to observe and interview target users. We might address the wrong task or deal with the wrong data abstraction. We might select an ineffective encoding or an ill-defined interaction idiom. We might have a slow algorithm. We might need to produce a better implementation of it. But as you can see, at each step, there are steps typically that we can take in order to validate our approach. Banally, simply, a slow algorithm can be analyzed in terms of computational complexity, and then after implementation, its implementation can be analyzed in terms of measurements of the resources, of the computational resources that the implementation is using. As we were trying to do in part 1, an encoding can be justified theoretically. And then once that is done, it can be validated quantitatively by, for instance, trying to invert the visualization going back to the original data tables. So issues of interaction design can be validated by laboratory studies, and then issues related to addressing the wrong task and even the wrong problem can be addressed by field tests, essentially, trying to understand, trying to do the last thing we were commenting upon, looking at real users in the wild, if you wish, doing their job, trying to collect evidence of the way they are using the system, finally observing adoption rates, even though all these steps really need to be looked into again critically, trying to understand, for instance, what the adoption of similar systems was before your system was considered, or whether you are essentially proposing a solution for a problem that might not be relevant to a given user community, but that might be relevant to a perhaps smaller but much more interested subset of users. That's, let's say, the very, very end of, it's a very, very interesting phase of the development of an interactive visualization system. There is a moment when really you need to complement the metrics you are getting from the system with a series of questionnaires that you provide to the users, because really because you are essentially trying to make sense of what you see them doing. You are trying to use your software, your interactive visualization system, as a very high bandwidth communication channel, communication and interaction channel, if you wish, between humans on one side of this channel, the human domain experts, with the models, with the machine intelligences in the middle, and on the other side of the channel, of the communication channel, you have yourself, in a way, trying to get this distilled knowledge, this distilled communication, this summarized or model-based summarized this information, this knowledge, distilled in terms of the models you have set up, so that you can close this communication loop with the domain experts. And again, it will be a very noisy communication channel, but communication will be interesting, typically. And that's the end of the talk.
Oh.
And I thank you for your attention.
So, Flora. Thank you very much for the talk. So, Flora, I'll do the first questions. I have many questions while the other people think. I mean, first of all, let me make a comment. When with Roberta and Antonio we planned this course, one thing which we realized, it is one sentence which you always find on all textbooks, is that a data scientist is someone who must be capable to extract information and present them to the final user, be it a scientist or a manager and so on, in an easy to understand way. And then you hit the reality. In fact, we have foreseen a course on data visualization in our let's say, formative process, I mean, and we have a problem to fill it, because as it always happens, every time you hit into something which is very interdisciplinary, like visualization, because visualization basically touches physiology, human perception, algorithmic skills, technical skills, and so on, you have difficulties in finding this type of people. And this is, I think, it's really a shortcoming. A second shortcoming which I find is that even if you train a data scientist to do advanced visualization, on the other side of the desk, you have people who are not even capable very often to understand a Cartesian diagram.
And who are typically very busy with, keeping up with, I don't know.
I want your comment on that, and then I have other questions, but I leave room to the other people. But I think it's something which is really often overlooked, because as we say in Naples, noi ce la cantiamo e ce la suoniamo, no? We sing it, we define what a data scientist must be, and then you hit against the reality of a world which is not adapting at the right speed at the new methods and the new reality and the new science. We form fantastic data scientists, we form fantastic data engineers, and on the other side there is a community which slowly adapts to these new technologies.
So on the one hand, I fully agree, there is a level of interdisciplinarity in all data science that is exacerbated in the domain of visualization. But again, yes, I fully agree with you. There is a moment in which your designed visualization meets the final user. Before that, ce la cantiamo e ce la suoniamo, in the sense that it really is, I mean, it's either adoption by a very different community that is interested in very different objectives than the ones you are looking at, and that might be speaking a very different language, or you really have no data. That's the dramatic thing. In Munzner's approach to validation, you really need to reach the implementation level, and that's halfway through. Let's say we worked recently to build a very large, well, a largish document-based visualization tool for a refinery, or for let's say people doing oil and gas, let's say. And the final users are really people who are fantastic at their job, people who are monsters, so to say, at keeping under control a very dangerous set of 50,000 variables that are measured every second, measured along around 500 kilometers of tubes, with aspects related to security that are hard to overemphasize, and with obviously very serious economic, for instance, consequences of the decisions they take. Communicating with those users, really providing a solution to their problem, and really addressing all the roadblocks, all the apparently minor difficulties that really affect this communication, right? The bandwidth, addressing the bottlenecks in this communication channel is a process that is full of surprises, that requires really understanding different languages, and really it's a way to learn lots of very, very interesting things. Yes. So I only have war stories to answer your question. I still have no. I only have scars, no solutions, but
I like scars, not solutions. Yeah.
I make a comment. I would like to thanks Marco for this nice talk. Well, visualization is something that has always attracted me so much since I was a PhD student. Probably you know the school of Anthony Arwind in Augsburg. He is one of the top scientists about visualization. And well, I would like to recall, well, the first example that you show us about the linear regression in the data. I mean, this is a kind of mission that was also in the book of John Tuckley on exploratory data analysis, the one that invented this topic, more or less.
yes.
Well, in the statistics, because everybody starts with the own point of view. So I'm a statistician, so I was attracted by the book of John Tuckley because it was the one that was saying Well, no probability. We have to follow the data, so data-driven procedures. So we have to build up a model starting by visual representation of your data. And so now, I mean, the best that you can get from exploratory data analysis that you can have good questions to make. So in some way, the visualization and the exploratory data analysis. So this is a very important step. It should help to submit the right questions. Sometimes, I mean, the ones that have that need some kind of quantitative data analysis, they put the real problem to you. But in order to transform this real problem into a very important questions, you need the visualization, you need the exploratory data analysis, something that you have to absolutely invest on. That definitely, I mean, it's also a better way to use than all kind of statistical learning or machine learning procedures afterwards if you have done a very good visualization analysis. I would like to suggest you to add in your example about linear regression to show the confidence band of your model fit, because in some way you can add a very important question, a very important point, because when you represent a model fit, you don't know whether this is a very good one, is accurate or not. And so your data and variation, well, it's the base of statistics. I mean, can sound, well, it's a good model fit or worse good model fit, then you can add up another piece of information, because if you add up also confidence band, you have more information about that. So, well, it's just a suggestion when you use this material for another webinar and so on.
Thank you.
It's nice.
I think you're raising a very, very crucial point. On the one hand, we have this very empirical way of looking at things. And yet, if we only limit ourselves to the empirical, if we don't have a plan, if we don't have a theory, if we do not see what we are looking at as a realization typically of, you know, a process that is generating our observations, and yet we are really interested in the mysterious thing behind the concrete.
This is the exploration, and then there is the other step from the statistical point is more inferential, inductive, and also for that you need the special visualization, because when you want to stress on a specific point that you want to transfer as a final result in terms of decision or in terms of forecasting, then again you need this requires another important step of visualization. How to present your output, your dashboard, or your results, and that should be less technical as possible. The first one for exploratory analysis should be very technical, and the second types should be more, I mean, quantitative storytelling, and so to tell the story to some people that are not, I mean, very expert or very technician. So it should be so all the aspect about psychological emotions and so should come as important steps. And also one other thing that you stressed was also interesting, the idea that well, this is a kind of dream that that the visualization. So we have already that the colors says of the shape of a kind of a symbol can tell you something about the data, about the quantitative number. But my dream is that, you know, we have already developed some methodologies, some kind of machine learning or statistical learning approach that will use, for example, if you have a clustering of time series, then you can have a clustering based on the model parameters, not on your data. So it's a way that simplify your data analysis, and that is gives also more accurate.
If I can comment on this, there is
yes, but what would be nice if there should be, I mean, in the future, something that you can have a kind of interaction between the cognitive aspect of a person that analyzes a visualization and model fit. So it's something that put together, I mean, a kind of, well, in the future we will arrive a kind of hybrid procedures where there is a kind of machine learning algorithm which combines some ideas that people, I mean, cognitive aspect that people can get from the visualization tools. So I think this is artificial intelligence is something we will arrive.
There is already something like that.
Yeah, well, I don't know, but I'm telling what is a dream. And,
no, but I can satisfy your dream. It has been done at Virtualytics by...
Yes, something like that, of course.
You know Virtualytics, you know, and Ciro Donald.
Yes, you can use the visualization and the way you interpret the results of visualization as input in an algorithm. Well, this would be very nice, I think.
So let me just repeat what you said, in perhaps in slightly different terms. On the one hand, the proper modeling and representation of uncertainties and of the degree of belief in, let's say, the parameterization, the model, let's say, that is in a way extracted from the data, is crucial exactly at the moment in which the rubber hits the road, at the moment in which you're speaking with somebody from a different domain, yes, somebody who is speaking a different language.
Yes.
Paradoxically, let's say, probabilistic/Bayesian approaches to visualization might be, on the one hand, more sophisticated algorithmically or technically, yeah, but also more practical, more concrete, exactly when you're speaking to, yes, a practitioner, an expert, an application domain expert, because people, yeah, think,
well, according to the logic of Bayesian, it should be like a way to define a new prior based on the cognitive aspect.
Absolutely, absolutely. And then, as you were mentioning, and Giuseppe was complementing, there is so much to know about the user.
Yes, yes. But furthermore, I would like to congratulate with you because you have chosen a very nice place to live. I've been in the areas of your company. You're in Spain, in your Alaska, and it's well, it's a marvelous, well, quiet place to. It's a good life there.
But you are in Naples, so you win.
Okay.
Before we go ahead, are there other questions from the students or from the colleagues who are hiding? If not, I have just two quick questions. The first one is the following. As you know, we were among the pioneers in exploring visualization in virtual environment many years ago. And we found great advantages in visualizing massive data sets in virtual reality, let's say. Do you know whether there is any progress in that direction? This is the first question. Second, how do you take into account the anomalies in the client? For instance, color-coded diagrams do not work with color-blind people. Mm-hmm. And how do you take this into account?
With respect to the first issue, caves and massive data visualization, there is work that's been done in a number of places. I know about results in remote sensing, so in navigating the contents of very large archives by organizing those image contents, those image catalogs by content, by signal characteristics, if you wish. there is quite a large amount of practical work being done, for instance, in security and communication data. The thing that probably I would like to see more there is a reflection on the theoretical aspects, you know, exactly, since you are putting in principle the user, you are immersing the user in the visualization. You really, in theory, are in the position of doing what you were mentioning before. So trying to analyze more of the state of the user, perhaps of their reaction. So that's something that probably can be done, and I'm sure that a number of parties are doing it. I will look into virtualytics as soon as the teleconference is over. The other issue is related to
color blindness.
Color blindness. So I have this anecdote. I don't know whether it was Schneiderman, but let's say one of the, you know, fathers of visualization. He's given his first color monitor, color display, and before turning it on, he's repeating to himself, color is complicated, we need to address it properly. Color blindness, of course, needs to be accounted properly, needs to be accounted for properly by considering the right color maps that can be interpreted by people regardless of their condition. Color is hard to interpret, hard to quantify. It produces crosstalk and confusion. We really need to treat it carefully, and then it turns on the display and it says, wow, color. So yes, color is a, on the one hand, it's a very, very strong ingredient, let's say, in a visualization. Today, it tends to be unavoidable, and treating it properly is still so hard that interactive visualization systems tend to let the final user freely choose between different color maps. That, I think, is more of a declaration of, you know, powerlessness than really a freedom and affordance given to the user.
Thank you. Other questions?